This is question 10 from C1 Winter 2010. And the part I really want to get to in this question is part C, so I'm going to go through parts A and B a little bit more quickly. So part A is find the coordinates and nature of each of the stationary points. Well, for this you just have to differentiate and set this equal to 0. So we're going to find y prime, and this will just be equal to 3x squared minus 12x there. Then we set that equal to 0, so 3x squared minus 12x equals 0. So if I just grab that, 3x squared minus 12x equals 0. And you can take out a factor of 3x now, so you can say either 3x equals 0 or x minus 4 equals 0. So x equals 0 or 4. Then for each of these you find the y value, so y equals, well, at x equals 0, y is going to equal 20, and at x equals 4, y is going to equal 64 minus 96 plus 20, which is negative 12, I think. I think I've got that right. And then these are our two coordinates, here and here. So the second part of the question was to find the nature of these stationary points, and to do this we take the second derivative, which is going to equal 6x minus 12. And then what we do is we plug in our x values. So at x equals 0, y prime prime, y double dash, the second derivative, equals, well, minus 12, so that is less than 0. So that's going to be a maximum. And at x equals 4, our second derivative here is greater than 0, so that's going to be a local minimum. And then we've got a sketch C in part B. Well, so we just draw some axes here quickly. And so the 2 points that are important are our maximum and our minimum. So our maximum is going to be 0, 20, and our minimum is going to be 4 and minus 12, roughly there. And our sketch is going to be a cubic graph that looks something like that. And the question says, given this has 3 distinct roots, find the range of possible values for k. So if we call this function here, if we say that, we call this function here f of x, then we can come all the way down to this function, this bit here, and rewrite this as f of x minus k equals 0. And this might seem more familiar to you now, because this is just a transformation. Basically, if we have a positive value of k, then this graph is going to move down, and if we have a negative value of k, the graph is going to move up. And we've got to find how big or small k can be to have 3 distinct real roots. Well, what are the conditions on the graph for this? To have 3 distinct real roots for this equation, we've got to have the graph crossing the x-axis at 3 points, as this graph does at the moment. So how far can we move it down before that's no longer the case. Well, we can move it down by this amount. And because we know that this is the coordinate 0, 20, we know we can move it down 20. And similarly, we can move it up by up to 12. So therefore, we know that k has to be greater than negative 12 but less than 20. And note it's not greater than or equal to or less than or equal to, because at those points, rather than having two distinct real roots given by a curve, you only have one, and therefore you only have two distinct real roots at those points. So this is the solution to part C.